Today we are going to get back and actually define some of the parameters in our system before we get into this quantitative framework of microphase separation for our 50-50 AB block copolymer mixture to C lamellae microphase separation. So this is lamellae, lamella. I'll probably confuse those in between, but just stay with me. So we're going to develop this quantitative framework for this 50-50 mixture, this flat interface between two phase separated states as we saw last time. But we needed to kind of now define some new parameters to account for the fact that now we're working with not homopolymers, but block copolymers, A and B types. So we are going to use this definition of capital N, number of segments, just going to be Na and B. So there's some polymer here, Na. So Na is equal to X sub A, so the degree of polymerization, effectively. There's also going to be some size of one segment. So AABB, the volume of the segment, we can approximate, again, as a sphere in general for a polymer chain, because usually we are this kind of random coil mess right here. Lambda is going to be our domain periodicity, so it's the size of the lamella in this case, but that domain periodicity will be different. So when we get to either cylinders or spheres, those will change. But again, we're only focused right now for this kind of lamella one side here, and then all my dashes on this side here. We'll also be using this capital sigma, the interfacial area per chain. So the total area of the interface divided by the number of chains. So essentially what we're thinking about here, this interfacial area per chain, is very similar to basically the area of overlaps between A and B. So when that interface, that interfacial area, that IMSDS, it's basically that area of those overlaps. So again, that's going to change depending on the, how elongated these chains are, how free they are, and then depending on, again, how unfavorable this chi AB is. So how large is this? And finally, this gamma AB is our interfacial energy. We're going to approximate this as a function of chi, as you see here, and temperature. So it's a really nice approximation. Now, I didn't derive this. I know you all love my derivations, and I'll be happy to do so in another video if you ask for it, but don't ask for it. But if you're interested, and if you don't trust me, please trust me, but you could go and actually find this derivation in a book by Frederick. So you can look that up. But anyways, so with all those definitions, we are now going to kind of take a look. So again, this is what we're looking at in our system. So for a single block copolymer, it has this kind of, again, periodicity, this length of our lambda divided by 2. Here, this is our IMSDS. It's going to have some surface area, interfacial energy. It's going to have some interfacial area per chain, and that's what we're dealing with. Again, size of the polymer here. Yep. So let's go ahead and develop a little bit of a qualitative understanding of what we're going to be working with before we get into kind of the energy contributions here. So we are going to assume that we're in the very, very strong segregation limit. So so basically we're saying that chi AB is going to be very, very large. So not much greater than 0, but again, approximately greater than 0, and chi ABN is going to be, large, very large and positive. So N is large, chi B is greater than 0. Again, so strong segregation limit, i.e., they were going to want to phase separate, because again, we don't want these AB. These AB interactions are very, very unfavorable. They increase our Gibbs free energy. So in this limit, there's not going to be enough entropic driving force to mix, because that's what's going to, we're either in the mixed state or the microphase separated state. So there's not going to be enough entropic driving force to mix. There's only this strong driving force to phase segregate. So the only type of phase separation possible, all A goes to one side, all B goes to the other side. So what this means practically, and again, it makes our derivation a little bit nicer and really kind of elegant and beautiful, is we can just look at the change in free energy, so determine the ordering. So we don't have to, we know that if I want to figure out what is the thermodynamic state of my system, the equilibrium state, I have to have my chemical potential in the disordered state equal my chemical potential in the ordered state to find that transition, when that occurs between my ordered state of that microphase separation versus the disordered state of just that mess. But if we assume that we're in the strong segregation limit and that there's only one type of phase separation possible, all A goes to one, all B goes to the other, we could just look at the change in free energy, delta G, in this transition. So we do not need to look at the chemical potentials of A and B like we did previously in Flory-Hugden. So let's think about the free energy components in the system. So we know that there's going to be this high chi AB, or chi AB is going to be large. So unfavorable, they don't, chi AB do not want to interact, and again, that's what drives these polymers to phase separate like this. We want to minimize those A-B interactions along this interface here. So we want to minimize that interfacial area, and that is going to scale with the number of A-B contacts. But what's going to happen here is the chains are going to want to elongate, move away from that interface. So their length is going to increase. They're going to elongate in order to decrease this projected area. So let's look at it a little bit slower. So I have a chain like this. I want to minimize really only around this IMSDS, IMDS, or intermaterial dividing circle, IMDS, excuse me. Only along here can I have my AB contacts. So if my chain is allowed to kind of relax, it could bump into A and B here, if you can kind of see. So if my chain is kind of free, but if I kind of take this into the extreme example and just kind of put like a single dot and it's just fully elongated, almost like our contour length, I'm only going to have one AB interaction at this intermaterial dividing surface. But what's the penalty here? Why don't we want to be at our contour length? Well, because my delta S conformation will decrease dramatically. So in terms of our energy competition, we're going to have to pay this energy penalty due to that decrease in conformational entropy. So it's really, equilibrium is going to be determined by this competition between a desire to minimize that interfacial energy, minimize the AB contacts, and to maximize that those chain conformations. So before we get into a more quantitative understanding, let's look at our next time in the next video. Let's look at our states. So I have a disordered state here, and I have our phase separated state right here. So in the disordered state, what do we have? Well, this is just kind of like our Flory-Huggins theory, right? So we have the delta G of mixing, which is equal to our kind of, the chi AB, fraction of A, fraction of B, et cetera, et cetera, et cetera. There's a KT. And then we also had basically our delta S of mixing term. And we know that delta S of mixing scaled as 1 over x1 and 1 over x2. So in my disordered state here, I know I'm going to have, this interaction. I'm going to have to account for that somehow, some way. But what's going to be the magnitude of this delta S of mixing? Well, I'm mixing two polymers, right? And we said that N is large. So Na and Nb are very large. Really, 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 it could be 100K, degree of polymerization. So is this delta S of mixing term going to be large in magnitude? No, right? Because we're scaling inversely here. So this delta S of mixing term is what really kind of pushes us to be in this state. These chi AB interactions want us to go into this state right here. Well, what else is happening? What can be pushing us towards this mixed state? So we know that this contribution enthalpic wants to go here. This one wants to go into the mixed state, but again, it's going to be really, really, delta S of mixing here is going to be very, very small, very in magnitude. So small in magnitude. So what about in this ordered state here? Well, we know, again, we want to minimize these, again, these chi B interactions. We want to minimize this, that kind of sigma, that interfacial energy here. So we want to minimize this. So again, that's the driving force to be in this state here. But what else is happening here? What else can be driving us to go into the mixed state? Well, it is, in addition to that delta S mix, it's going to be this delta S of stretching. So again, the material does not want to be, your polymers do not want to be in this very elongated state. So that stretching term is very, very unfavorable. So it will not want to be in the ordered state. It will want to be pushed into the disordered state. So these are going to be kind of the big, energy contributions that are at battle here. So, and in fact, we'll see that we could almost neglect this delta S of mixing. So really the true driving force to be in the disordered state is going to be solely due to stretching, but we'll see that in a little bit later. So next time, quantitative derivations, really, really fun analysis, and we will see that coming up in a little bit. All right, I'll see you all in the next video. Thanks. Bye.